Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of orbital mechanics, and in particular, we're starting to put things together so we can finally get to the idea of what it means for one body to orbit around another body. Let's go ahead and get started. Now, one final piece of the puzzle has to do with the act of falling. And we've talked about Newton's three laws. We've now included the concept of universal gravitation. And now we need to discuss the idea of what it means for a body to fall. Now, I know this sounds trivial. People fall, things go from the high places to low places. But one of the questions that the ancient Greeks pondered is, do all objects fall at the same rate? Essentially, if you have a very heavy object and a very light object and you were to drop the two, would they hit the ground at the same time? So in their idea, or sort of like a brain experiment, if you would, they thought of the idea of a hammer or some very, very heavy object like a hammer and something very lightweight like a feather. Now, obviously, if you think about it, a hammer is very heavy, a feather is very lightweight, and so therefore they should not hit the ground at the same time. A hammer, heavy, falls fast. The feather, light, falls slow. That was the idea. To them, it was almost silly to conduct the experiment. But Galileo comes along, and Galileo felt it was important to actually conduct experiments. This is the scientific method. And what Galileo did was he dropped objects of different masses. He dropped objects made out of metal versus objects that are made out of cork. Cork is very lightweight, the metal is very heavy, and he didn't quite drop them. What he did was he would roll them down an inclined plane. And the idea is that he would time how long it would take for the object to roll to the bottom. And so what he discovered was when you had something round made out of metal versus something round made out of cork, that it would actually be that they would all roll down the inclined plane or fall at the same rate. So something heavy and something light would actually fall at the same rate, which of course doesn't seem to make sense. Now, wouldn't it be nice to actually drop something like a hammer and a feather to be able to see how this plays out? And what we'll find is that there's some features to the feather that need to be at least explored a little bit further before we can see why it is that the answer is actually yes. Now, a little while ago, we shot some video here in the studio of actually dropping several objects and seeing how they fall and if they do fall at the same rate. Have a look. So one of the most important ideas related to the concept of orbiting bodies has to do with falling bodies. And there's a particular demonstration that seems a little counterintuitive that we'll explore here that actually goes back to the time of the ancient Greeks. Now, if you think about it, something very heavy falling to the ground should fall with a particular acceleration as it falls to the ground, and something very light should fall with a much less acceleration. So in the minds of the ancient Greeks, they thought of something very heavy, maybe a big rock or piece of metal. What we're going to do today is use just a piece of steel. This is a weight from a physics lab, and it's 1 kilogram, and on Earth it weighs 2.2 pounds. You can see that it has some heft to it. So imagine dropping something heavy like this, and in the minds of the Greeks, something that was very light would be something like a feather. And a feather is, of course, something that has a minimal amount of weight, and when you drop it, of course, the idea is that you would think that the feather would fall slower with a lesser acceleration because it does not weigh as much. Now, rather than using a real feather, we're going to use a stunt double, just a piece of paper. You see, we'll christen it the feather here, and you'll see in a minute why we're not going to use the real feather. So what if we were to drop the feather or the sheet of paper with the heavy block here, and what we'll do is we'll see which one hits the ground first. So you can see that the idea is that when we have something that's very heavy falling to the ground, it reaches the ground faster than something very lightweight. Now, when you drop the feather, though, what you'll notice is that there's something interesting about the way that it falls that seems to be a contributing part of this. For instance, if I drop it again here, you can see that it has a motion to it that is not quite as direct. It sort of meanders its way down to the ground. And the reason why it does this is because of air resistance. As the feather pushes through the air, it has to push the air out of the way because of the shape of the feather itself. We call that the aerodynamics of the feather. And so the pushing of the air out of the way is impeding how it falls. And so you can make the argument that they don't hit the ground at the same time because of that. So what we're going to do is we're going to take away the air resistance. We're going to make the aerodynamics of the feather similar to the falling heavy object. And I'm just going to loosely crumple it up, if you will. Now, the aerodynamics is not a matter or not part of the situation anymore, but the important thing is to remember that its mass has not changed. By crumpling it up, it still has the same amount of mass as it did previously. Now, what you'll notice now is that something lightweight, something fairly heavy dropped from the same height are going to hit the ground at the same time. So this was a conundrum. Why is it that something very heavy and something very light hit the ground at the same time? It seems counterintuitive. Heavy objects should accelerate or fall faster, and lighter objects should accelerate with a lesser acceleration and fall slower. So you can see clearly that the problem with the feather was the fact that you have air resistance. The feather has to push the air out of the way, and when we crumpled up the feather or the piece of paper that was the stand-in, you can see that it actually was that both objects hit the ground at the same rate. But the ancient Greeks would have been upset with this because in the experiment that we did that you saw in that clip is that we crumpled up the feather, and to them they would have felt like that was somehow cheating or altering the experiment. So what if we could do it without crumpling up the feather? What if we had the ability to drop an actual heavy object in a feather and not have the air be a problem? So obviously you would want to take away the air, and taking away the air is not something we can do here on Earth. But it turns out that in the late 1960s and early 1970s, we were frequently going to places, or at least one place in particular, that did not have any air. And on the surface of the moon, there was an experiment that was conducted that will show you what happens when you drop a hammer and a feather. Let's have a look here.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Okay, so we're going to pause for a moment, and then I'm going to show you part of that all over again. But the second time I want you to watch it, we're going to just cut right to the part where he drops. Here's what I want you to pay careful attention to. The video that you saw, and that you'll see again in a second, is not slow motion. This is full motion video. Remember, they're in the environment of the moon. The moon has no air, and of course, the moon's gravity is weaker than on the Earth. So it is full motion video. You'll notice also that they both will fall and hit the ground at the same time, but it looks as if they are in slow motion, and we'll talk more about that in just a minute. When the hammer hits the dirt, you'll notice that even the handle falling over into the dirt seems to be slow motion video. So the feather is a falcon feather because the vehicle standing behind Dave Scott there was called the Falcon. Now let's watch this a second time. Watch how, again, it's full motion video, but notice how they both fall slowly, they both hit the dirt, and even how the handle hits the dirt. Watch how it looks this time around here.
And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
So there's something about that video that just seems counterintuitive. A hammer and a feather should not hit the dirt at the same time. Obviously something heavy you would think would fall fast and something lightweight would fall slow. But it turns out that the heaviness or the mass of the two makes no difference. They hit the ground at the same time. So let's find out why. It turns out that Isaac Newton would have made a prediction that would help us. Let's look at the math that goes behind this. So Newton, or what we call Newtonian mechanics, will explain what's going on. And forgive me, we're going to look at some math here, but we'll try to make it easy. So why is it that the hammer and the feather both hit the ground at the same time? In other words, why do all objects fall at the same rate regardless of their mass? Well, let's start with a couple of ideas. Let's assume that we have a large mass and a small mass, and the large mass, let's say, is, if you were doing it here on Earth, is the mass of the Earth, and the small mass, let's say, is the mass of the hammer. So capital M, lowercase m. Now, what we're going to do is we're going to calculate what is called the acceleration due to gravity. What that simply means is whenever you drop something, things will accelerate because of the force of gravity. So it's the acceleration due to the force of gravity, and we're going to call that lowercase g, even though it's acceleration. Now, the formula we're going to use is Newton's second law, which is F equals ma, but remember the acceleration is due to gravity, so we're going to substitute in the letter g, and it ends up being F equals mg. So force equals mass times the acceleration due to gravity. Now, what we also know is the universal law of gravitation is F equals gmm over r squared. Now, this force and this force are the same thing. So in the world of mathematics, if this F and this F are the same thing, then what we can do is set what they're equal to each other. So mg now is equal to gmm over r squared. So if these two equal each other, then what they represent is also equal to each other. So what I'm going to do is set each of these equal to each other. Now, notice the gmm over r squared is equal to mg. I'm going to put in some symbols and some explanations to go with the variables. So lowercase m, remember, is the mass of the falling object. Capital M is the mass of the Earth. And r squared is the distance between their centers. Now, you'll notice the lowercase m on this side as well, this mass of the falling body, or the mass of the hammer. Now, if you know anything about the math, the basics of math of algebra, what you'll notice is that I have a variable on the right side, this lowercase m, and I have a variable on the left side, also lowercase m. So what that means is that because the lowercase m is on both sides of the equal sign, that means they cancel. In other words, these two lowercase m's go away. What you'll notice, though, is if the lowercase m's go away, then you're just left with g capital M over r squared. So what that means is the acceleration due to gravity only depends on the constant for gravity, the mass of the body that you're falling to, and the distance between their centers. Notice the mass of the falling body no longer matters. So what that represents is you could drop something very massive and heavy like a hammer, something low mass and not so heavy like a feather, and their acceleration, how they fall, has nothing to do with their mass. A heavy object, a light object are both going to accelerate the same. So on the moon, of course, the only thing that's really different is it's the mass of the moon in this case. And of course, the moon's physical diameter, its size is different. So when you adjust the r to be for what the moon's value is, and you adjust the m to be for what the moon's value is, you get an acceleration due to gravity that is different than here on Earth. On Earth, this value for g is 22 miles per hour per second. What that means is every second that something falls, you fall another 22 miles per hour faster. So if you were to fall for 1 second, by the time you hit the ground, you're traveling at 22 miles per hour. If you fall for 2 seconds, by the time you hit the ground, you're traveling at 44 miles per hour. Fall for 3 seconds, you're falling and you hit the ground at 66 miles per hour. On the moon, because the m is different and the r is different, the g is different. It is 1/6 what it is here on Earth. So in that video, it may look like the hammer and the feather are in slow motion, but they are actually falling at full speed. They're falling at regular speed for what the moon is, but on the moon, because the acceleration due to gravity is 1/6 what it is here on Earth, what that means is that when the hammer and the feather fall on the moon, they're going to fall with an acceleration due to gravity that's less, and so it looks like it's slow motion. But that also means the astronauts don't weigh as much. They weigh 1/6 as what they would here on Earth. So notice on the moon, take away the air, don't crumple the feather. With the lack of air or no air resistance, you can have the very, very obvious fact that all objects fall at the same rate. Now what we're going to see is how falling bodies play a major role when it comes to orbiting bodies, and we'll put it all together in the next video. We'll see you then.